especially for talking for St. Petersburg conference. Yes, and Vladimir Lifshitz is from deep St. Petersburg intelligentsia. So, and it just moved to the States, and we met the first time we met actually probably was Stanford in the end of the 80s when Vladimir worked with John McCarthy. And then I heard that Vladimir got the position, just a very honorable position in University of Texas, Austin. And then I asked why Austin, and I was told that, come on, I was just very new in the States. And they said that Austin is the most pleasant place in the whole Texas. So don't worry about this. This is an excellent place, and Vladimir will fit there very nicely. And that's what happened. So Vladimir is one of the realist, the gods, and if not the god, in logic programming, with some impossible awards like the most influential paper of the 20 years, and something of this kind. And yet, this is all based on the very noble foundation of constructive logic and the mathematical logic base, which Vladimir got in Lomi and Leningrad, St. Petersburg. And it's a honor for us, honor for me, honor for the conference, and a big pleasure to listen to Vladimir Lifshitz. Please.
Thank you, Sergey. Thank you. Many thanks to the organizers of this conference in honor of Vladimir Pavlovich Alivkov, and for giving me a chance to speak here. So I'll be sharing my screen with you. Okay, you see it?
Yes.
Okay, so let's see, my screen says sharing is paused. Bring your shared window to the front. Do you see the changes in the screen? Like moving from one page to another?
No.
Oh, okay.
It's still.
Oh, okay. It's it should.
Oh yes. Now
you see it. Okay.
It advanced. Yes.
All right. Okay. So this talk is about logical analysis of the functionality of logic programming systems. Specifically, we are going to talk about one such system called Klingo, which was designed and implemented as in maintained now at Potsdam University in Germany. And I start with an example of what Klingo does. So here on the left, you see an example of a file that we give to Klingo as input, a logic program, these 3 lines here. And what Klingo returns are these 2 lines, 2 answers. And to understand the relationship between the logic program and the output that Klingo produces for it, we're going to think of this input as a representation of 3 propositional formulas. So you can think of each of these lines, each of these rules, as an implication written backwards, with the symbol colon dash in the middle being this implication arrow turned backwards, so that the first line corresponds to the implication if Q then P, the second to the implication if not R is then Q, and the third to the implication if not P then R. So here in this line you can see this input logic program written in the usual syntax of propositional formulas. So if you think of truth assignments that satisfy these formulas, out of those 8 ways to assign truth values to PQR, there are 4 that satisfy all 3 formulas, 4 models. And here they are represented by sets of ground atoms. What is customary in the literature on logic programming is that you represent a truth assignment by listing all atoms that get the value true. So the singleton R here represents the truth assignment, which assigns the value true to R and the value false to the other 2 atoms. And PQR, for instance, the truth assignment that makes all 3 atoms true. So these are 4 models of this input that we gave to Klingo. And we see that what Klingo returned were 2 of those models. It said that R and PQ are 2 answers. And it did not return PR and did not return PQR. So what we're interested in, if we want to understand what it is that Klingo is doing, is how these first 2 models are different from the others. What additional feature of these models make them appropriate for the output of Klingo. And this talk is about 2 answers to this question that have been proposed and the relationship between them. And before I talk about these 2 answers, I want to point out that there is a case when, for some particularly simple inputs that you can give to Klingo, there is a very simple answer. This easy case when every formula is a definite clause written as an implication. So for instance, if you look at this set of definite clauses, P, if R, then Q, if P and Q, then R, here what they look like in the syntax of logic programming. And here's the output of Klingo. It gives only 1 answer. And what actually happens whenever you give to Klingo a set of definite clauses, a set of definite clauses has a least model, a model which is viewed as a set of atoms, a subset of every other model. And in this case, the least model of this set is P. You can also make R and Q true, that will be still a model, but the least model is just a singleton P, and that's what Klingo returns. And that is generally true. Whenever the input that we give to Klingo is a set of definite clauses, it will return 1 answer, its least model. So the question we are going to address is what happens in a more general case when the input is not a set of definite clauses. And that corresponds to the case as in the input that you saw on the previous slide, when there are negations to the right of this if symbol. So one answer, one explanation of how 2 of those 4 models that you saw in the first example are different from the others is based on the idea of program completion. So imagine that we have a finite set of propositional formulas of this form, F arrow A, where A is an atom, and F is an arbitrary propositional formula. In particular, it can be the constant true, in which case the corresponding formula would be simply an atom. So the completion of such a set of formulas is the set of equivalences of this form for all atoms. So that for every atom A that we deal with, we write this equivalent, saying that A is equivalent to the junction of the antecedents of all formulas, all implications in pi with the consequent A. And this completion, the set of equivalences, it actually is stronger than the set pi itself. This completion entails pi because if you take the body, the antecedent F of any of these implications, F will imply this disjunction stronger than disjunction, and then the implication right to left will give us A. So using the completion, we can derive A from F for every such implication in pi. And it turns out that if we apply to our first example, that it is actually stronger, and what it does, it eliminates the two models that Klingo considers bad, that it does not return as answers. So here you see again this example that you saw before, and here it's completion. In this case, for each of the atoms occurring in the program, there is exactly one implication in pi that has this atom and the consequence. So each of these disjunctions here is simply one of these formulas F. So the only implication, the consequent P is Q implies P. So we say P is equivalent to Q. The only implication with the consequent Q is this one. So we write Q is equivalent to not R. And similarly, we turn this implication to equivalence. And if you look at models of completion, there are exactly two of them, R and PQ. And the set PR, for instance, one of the models of pi, which Klingo rejects, does not consider an answer, is not a model of completion. It violates the last of these equivalences. And here's another example. This is actually a definite program. Q implies P, R implies P. So here we have two implications in our set with the consequent P. So according to this general definition, the equivalence with the left-hand side P will have this junction of two formulas. We'll say that P is equivalent to this disjunction Q or R. And Q and R are not a consequence of any implications at all. So each of them we write in the completion is equivalent to the empty disjunction falsity, which I denote by bottom. And the only model of completion is the one that makes P, Q, and R false. And this is, of course, the minimal model, the one that Klingo would return in this case. This idea of completion actually has a simple intuitive meaning. If you think of all these formulas in pi with the consequent A as sufficient conditions for A being true, what the completion equivalence says is that all these sufficient conditions collectively are also necessary. If A is true, then at least one of these formulas F is true. That's what these implications left or right in the completion formula tell us. One other way to think about the intuitive meaning of completion is in terms of supportedness. So let's look again at a set of propositional formulas of this form F implies A, where A is an atom. And this time we don't even need to assume that the set is finite. In the definition of completion is what was important. Let's go back for a second. In the definition of completion, it was important that the set is finite. At least for every A, you should have only finitely many rules with the consequent A, because we want to form this disjunction. And so unless we want to use infinitely long formulas, we need to assume that the set is finite. Here, pi is an arbitrary set of propositional formulas of this form. And a model of the set pi, viewed again as a set of atoms, is called supported if every atom in this model X, in other words, every atom that we declare true, is the consequent of one of the formulas in pi, which are satisfied, I should say, by this model. In other words, for every such formula, for every such atom which we included in X, there is a reason for that. There is an implication with the consequent A, whose antecedent F is true according to this model X. And it's easy to see that supported models, in the special case when pi is finite, so we can form the completion of pi. Supported models of pi are exactly the models of completion, because these implications from left to right here, they exactly express supportedness. If A is true in our model, then at least one of these antecedents F of implications with the consequent A should be also true. So if we go back again to this example, first example, and want to explain what's wrong with the model PR, what is the reason why Klingo does not return it as an answer, we can say that this model is not supported. Specifically, the atom R, its presence in the model is not supported. We do have an implication, the consequent R, but its antecedent is false in our model. So it does not provide support for R. And here you can see two more examples of completion. And what's interesting about these examples is that in these cases, the set of models of completion is actually different from the answers that Klingo generates. So these examples show that that interpreting the output of Klingo as the set of supported models or models of completion is actually not a perfect answer. Sometimes it does not correctly describe what Klingo does, which is what will lead us to the second alternative explanation of the meaning of the output of logic programming systems. So consider this set of two rules. If Q, then P. If P and R, then Q. Here's the completion. P is equivalent to the antecedent Q of the only implication, the consequent P. Q is equivalent to the antecedent P and not R of the only implication with the consequent Q. And R is equivalent to falsity bottom because R is not the consequent of any of the implications, even implications. And this set of formulas, this completion, has two models. One possibility is to declare all three atoms false. And yet another possibility is to say that P and Q are true and R is false. So according to this completion theory, Klingo was supposed to return two answers, the empty set and PQ, but it generates the empty set only. Somehow PQ is not appropriate as an answer, according to Klingo. And here's another example of this kind. What's interesting about example 4 is that this is a definite program. There are no negations in the antecedents. And here again, if you form a completion, it will have two models. Singleton P is, of course, the least model. And that's what Klingo returns. And program completion has also this one other model, PQR. You can say that all three atoms are true, and that will satisfy not only the given implications, but also all three equivalences. So that what's peculiar about program completion is that not only it does not perfectly describe what Klingo does, but it also does not agree with our simple explanation for the easy case of definite programs. So all that leads us to a different theory. Now, so let's now forget about completion for a while, and I will give a definition of a stable model. And this definition is actually more general than the definition of completion, in the sense that it is applicable to arbitrary propositional formulas. We'll define here what a stable model of an arbitrary set of propositional formulas is. You don't even need to assume that the given formulas are implications with an atom in the consequent. So there's this auxiliary definition that we need to give. So let me tell you that a nice thing about this definition of a stable model is that it's more general, and it, in a sense, it perfectly corresponds to what Klingo is doing. One unpleasant thing about it, at least about the version of the definition that I give here, is that it is not so easy to explain its intuitive meaning and the intuition behind it. To me, it looks in this very general form, when we talk about arbitrary propositional formulas, it looks somewhat cryptic, but the definition is not long, so I'll give you a definition. So we need to define we're going to define for any propositional formula F and any set X of atoms, what we mean by the reduct of F with respect to the set. And the reduct of F with respect to the set is another propositional formula which is obtained from F by replacing some of its subformulas by bottom, by falsity. So it's going to be shorter than F. It's really a reduced form of F. And here's what we do. To form the reduct of F relative to X, we find, first of all, in F, all subformulas that are not satisfied by X, that get the value false, if we assume that the atoms in X are true and all the other atoms are false. And we take only the maximum, the largest of these subformulas. So if one subformula which is false is a part of a larger subformula which is false, we only look at the larger subformula. And these are the parts of F that we replace by bottom. They, of course, disjoin these maximal subformulas. So in this example here, I look at the formula not P implies Q, and I calculate its reducts relative to all four subsets of the set of atoms PQ that occur here. If our atom set X is empty, in other words, both P and Q get the value false, then the whole formula is not satisfied. So the whole formula is replaced by a bottom, and this is the reduct. If P is true and Q is false, then not P becomes false and Q becomes false, but the implication is true. So the antecedent and the consequent are the two subformulas that need to be replaced by falsity. So here it is, the reduct. If, on the other hand, Q is true and P is false, then P is the only part of this formula which gets the value false. So this is the reduct. And finally, if P and Q are both true, the only subformula of this formula which is false is not P. So here's the reduct. So now we say that X is a stable model of a set of propositional formulas if it is minimal in the sense of set inclusion among the models of the reducts of all formulas in F. So it's kind of a fixed point definition, not a constructive definition. What it says, if you want to check whether X is a stable model of pi, you calculate the reducts of all formulas in pi, just as I did it a minute ago for not P implies Q, reducts relative to X. And then you check that X that you started with it satisfies all these formulas, and that is minimal with respect to set inclusion. In other words, that proper subsets of X do not satisfy these reducts. So in this example, for instance, the only stable model of this set is Q. So here, in each of these four cases, I found all minimal models. So in the first case, since this reduct is unsatisfiable, there are no models. This is a tautology. Bottom implies bottom, so its minimal model is the empty set. This reduct is equivalent to Q, because not bottom is a tautology. So Q has two models, Q and PQ, if you use only atoms PQ, and this is the only minimal model. So it is stable. You see this, it is minimal model, and that's exactly the set that we started with. So the fact that we started with singleton Q and got singleton Q shows a stable model. And here, again, this formula is tautology because it has falsity in the antecedent. So PQ is a model, but not minimal. So this is the only stable model according to this definition. And this is, in a sense, when we say that what Klingo calculates is the set of all stable models of a given input, is in a sense of a perfect description of what Klingo does, except that we need, of course, to discuss in more detail what kind of inputs Klingo accepts and how these inputs are represented by propositional formulas. So here's a brief history of the subject. So the idea of the role of least models for understanding the role of definite clauses in logic programming was proposed in 1976. Completion was defined originally in 1978 for a more limited set of formulas. In this definition of completion, the antecedent was supposed to be a conjunction of literals. But a few years later, other authors noticed that in 1984, that the definition of completion makes perfect sense if the antecedent is an arbitrary formula. Actually, I must say, in all this work, all that work on completion was done for first order formulas with variables and quantifiers, something that is not important for this talk. Stable models were originally defined for in 1988, independently by several authors. And again, like in the set of case of completion, it was defined first for rules with this body or antecedent of the implication of a special form, and then extended to arbitrary propositional formulas a few years later in 2005. So in a way, this story is similar to the story of completion, except that extending the definition of a stable model to the case of arbitrary propositional formulas was a lot more difficult. With completion, it was just a simple observation. You don't need to change anything in the 1978 definition of completion. Here, the definition of the reduct proposed by Ferraris in 2005, which I just quoted, it actually looks very different and much more cryptic than the definition of completion of the reduct given originally in 1988 for the special case. And it's not obvious at all that even though the reducts mentioned in these definitions are different, the class of stable models is the same in the case covered by the 1988 definition. So it was really an interesting, remarkable achievement. And then the study of the relationship between these two theories, these two concepts, completion and stable models, it started in 1994. The first result of this kind was published, which of course covered only rules of a special form, because at that time, stable models were only defined, the general definition of a stable model was not yet given. And then there were many other publications. We're going to talk a little later about why this is an important question, the relationship between these two concepts, and why it was studied by many authors. It was generalized and extended, this Farsh theorem, in many ways. And what you see on one of my last slides soon, which will give the technical content of the new material, is the latest result in this series. So that was 1994 when this work started. And Klingo was, the first version of Klingo was made public around 2007. And it's, so in a way, when I said that we're trying to understand what Klingo is doing, and that's why we invent stable models, that was misleading, because actually what happened is that the designers of Klingo saw the definition of stable model and said, oh yes, we want to create a system that will generate stable models. That's what actually happened historically. And we'll talk a little later about why they decided it's a good idea to do that. So that's actually the next thing I want to talk about, why Klingo is an important system, and why the question about its relation, the relationship between stable models and completion is an interesting question. But before I do that, I want to share with you an interesting quote from an old paper by Alfred Tarski, where he discusses a more general question about how mathematicians choose which problems to study in general. So it's a long quote, please bear with me. Being a mathematician, Tarski writes, I have had the opportunity to attend many discussions between specialists in mathematics where the problem of applications is especially acute, and have noticed on several occasions the following phenomenon. If a mathematician wishes to disparage the work of one of his colleagues, say A, the most effective method he finds for doing this is to ask where the results can be applied. The hard-pressed man with his back against the wall finally unearths the researches of another mathematician, B, as a locus of the application of his own results. If next B is plagued with a similar question, he will refer to another mathematician, C. After a few steps of this kind, we find ourselves referred back to the researchers of A, and in this way, the chain closes. Speaking more seriously, Tarski continues, I do not wish to deny that the value of a man's work may be increased by its implications for the research of others and for practice, but I believe nevertheless that is inimical to the progress of science to measure the importance of any research exclusively or chiefly in terms of its usefulness and applicability. We know from the history of science that many important results and discoveries have had to wait centuries before they were applied in any field. In my opinion, there are also other important factors that cannot be disregarded in determining the value of a scientific work. It seems to me, Tarski says, that there's a special domain of very profound and strong human needs related to scientific research, which are similar in many ways to aesthetic and perhaps religious needs. And it also seems to me that the satisfaction of these needs should be considered an important task of research. And then he says, hence I believe the question of the value of any research cannot be adequately answered without taking into account the intellectual satisfaction which the results of that research bring to those who understand it and care for it. It may be unpopular and out of date to say it, but I do not think that a scientific result which gives us a better understanding of the world and makes it more harmonious in our eyes should be held in lower esteem than, say, an invention which reduces the cost of paving roads or improves household plumbing. So as to the this question that we're going to talk about, the relationship between completion and stable models, I can say that, yes, many authors who studied this problem were interested in it because of this intellectual satisfaction that brings them. But in this particular case, I can say more. It's not really paving roads or household plumbing, but there is another reason why we're interested in these questions. So first of all, there is a reason why Klingo and similar systems are practically useful, and why much effort was invested by programmers in many universities and companies actually into the creation of systems for calculating stable models and making them more efficient. One of the reasons is that Klingo can be used to solve computational problems using the following idea. You encode the problem that you want to solve by a set of rules that you can give to Klingo in such a way that the stable models of those rules will correspond to the solutions. And then you run Klingo, look at the answers and say, these are answers to my question. And this is this kind of use of stable models is known as answer set programming. And you see here a quote from an invited talk at last year's International Conference on Logic Programming, which mentions various areas to which this method has been applied. So household plumbing is not here, but some of these items are in that spirit. And then also you can ask me, okay, you can say, okay, so Klingo is useful, but if completion is not a perfect explanation of what it does, why do you care about completion and its relation to stable models? And the answer to that, or part of the answer, is that if your program for which you want to find stable models is in that class of programs for which models of completion are identical to stable models, then you can use a set solver, a system that calculates models of a set of propositional formulas to find stable models. You simply take your program, take a set of applications, form the completion, convert it to closal form, and give it to set solver as an input. And this is an idea that plays an important role in the development of systems like Klingo, and this direction in the design of systems for calculating stable models is known as set-based answer set programming. Now, the theorem that I wanted to share with you. So take a set of propositional formulas of this form, F implies A, where A is an atom. What do we know about the relationship between stable models and supported models? We know first that every stable model is always supported. So the only question is under what conditions we can assert the converse, that also all supported models are stable. And to do that, we should look at what is called the positive dependency graph of our set of propositional formulas. It's a directed graph. Its vertices are the atoms occurring in the formulas. And it has an edge from an atom A to an atom A prime. If there is a formula F implies A in your set pi, so that its consequent is the first atom A, and the atom A prime has a strictly positive occurrence in F, which means that A prime has an occurrence which is not in the scope of any negation and not in the antecedent of any implication. So then have an edge. And what we know is that if this positive dependency graph has no infinite paths, then all supported models of pi are stable. in the special case where now set is finite, so that we can talk about the completion of the program. Also, the graph is finite, and the only way for a finite graph to have an infinite path is to have a cycle. So to say that the finite graph has no infinite paths means that it is a cyclic. So the obvious corollary is that if the SPI is finite and its positive dependency graph is a cyclic, then all models of the completion are stable. So here's what happens when we apply it to our 4 examples. You remember that these are 4 programs. For the first 2, completion, stable models and models of completion were the same thing. And the last 2 examples, we had some redundant, spurious state models of completion that were not stable. Here you can see dependency graphs. So for instance, in example 3, you can see that P depends on Q. We have this formula with P in the consequent and Q as strictly positive in the antecedents, have an arrow from P to Q. And here in the second implication, we have Q in the consequent and P, which is strictly positive in this conjunction, P and not R. And R is not strictly positive, it's negated. So we have also an arrow from Q to P. So I have these 2 arrows from P to Q and from Q to P. There is no arrow from Q to R because this occurrence is negative. And you can see that these graphs really are cyclic, and these are not. So this theorem that you saw, it explains this phenomenon. My talk, unless unlike the previous talk in this meeting, does not have, I must confess, very much to do with the work that Vladimir Pavlovich Rivkov has been doing. But there is actually something related to, in this theorem here, if we go back to it, that reminds me of the good old time that Vladimir Pavlovich and I spent together in room 28 of Lomi in Professor Shanin's seminars. It's a mention of strictly positive here. You see, this concept of a strictly positive occurrence is not really interesting as long as we're doing classical mathematics, because when we apply equivalent transformations, like when we drop double negation in front of an atom, an occurrence that was not strictly positive can become strictly positive. So in classical logic, the important difference is between positive and negative occurrences. And the difference between strictly positive and what is not strictly positive is actually something that is important in intuitionistic and model logics. So this concept of strictly positive occurrence is something that I learned many years ago from my teachers in room 28, including Vladimir Pavlovich. And you can find details in this research note, which is not published yet, but is posted online. Thank you for your attention.
Yes. Very good. Questions, please.
Serежа, можно мне поставить question? I have a question, Volodya. Difficult cases for Klinger. They are given in some way by the theorem and the corollary, if the premises are not satisfied, so the case will be difficult.
Yes, so Klinger does not allow you to encode arbitrary propositional formulas unless you use some abbreviations for subformulas. But there is actually, there are formulas, for instance, that are allowed in the input of Klingo, for which it's important, for instance, to have a definition of a stable model that is more general than the original 1988 definition, when the antecedent of the implication was a conjunction of literals. One thing you can do there is, for instance, have a double negation. You can write in Klingo, P if not Q. This rule, by the way, its meaning is not the same as the meaning of P if Q. And by the way, which reminds me of a kind of interesting episode. Before the creation of Klingo, I corresponded with designers of kind of one of the predecessors of Klingo, an earlier system that had similar functionality, which was called S models. And I looked at the program P if not P, and I saw that the answer that it returns was the same as if we didn't have this double negation. And I remember it from my young days in room 28 that double negations are important. So I sent an email to the designers of S models saying, isn't something wrong with your system? It doesn't notice this double negation. And the designers of the system said, yes, that's a bug. Thank you. We'll correct it in the next version. Also, the syntax of Klingo programs allows us to write one level of implications in the antecedent. So we can write something like, if P implies Q, then R. You cannot write three levels of implication, but some degree of generality is essential for understanding Klingo. I don't know if it answers your question.
Yes, you give some details, yeah.
Mm-hmm.
More questions, please.
It's Vladik. Thank you very much for a very interesting talk. How kind of, this is like sufficient conditions. To what extent are they necessary? Is it like?
No, they are not necessary. And actually, in some applications, you do need stronger theorems. As a matter of fact, this theorem that I showed to you, it's just a little bit stronger than something that was already known. This graph, dependency graph, was constructed a few years ago in a slightly different way, and it gave a more limited condition. And what happened is that my co-author, Jorge Fandino, and I, we worked on something really related, really motivated by designing a new software tool, which required generalizing that old version. So that is, in the process, we noticed that this definition of positive dependency graph can be improved. So our theorem will become a little more general. But then it turned out that even that more general form that I showed you is not sufficiently general for our application. So we made it even stronger than that. We have a series of more and more involved syntactic sufficient conditions, but not really a nice even on-leaf characterization.
Thank you very much.
Hi, could I ask a question? Hi, this is Sam Buss. Thank you for the talk. That was very nice. I wanted to ask about the computational complexity of stable models. It looks to me like they're probably in co-MP, if that's correct. And I was wondering, is this known to the exact computational complexity? What does it say about SAT solving for it? Yeah.
Let's see, for the general case, I think the existence of a stable model is in the second polynomial class.
Mm-hmm.
Yes, that's what is.
And does that allow it? Can you still use SAT solvers for finding stable models? Or is that
the thing with there are yes, sometimes you can, under some conditions. Yes, there are theorems, for instance, about the possibility of replacing some programs of the kinds when it is in the circuit complexity class, one can replace them by syntactically simpler programs which can be encoded in terms of completion. So the answer is yes, under some syntactic conditions.
Okay, all right, thank you.
More questions, please? Well, there'll be very nice discussion. Well, and let's thank the speaker again. Yes.
There's one, this is not, I have a colleague in Potsdam, computer scientist, that does this kind of work, but not the work that this guy was talking about, actually. But